Golly, golly. Guys, what is going on? We are starting a new series, the EVM series with Alchemy University. Guys, this is a totally free course. I've actually started the course. I was like, you know what? I should definitely share some of the journey and just share. I love to learn, you know what I mean? And especially with blockchain stuff, this stuff could be a little bit nuanced. You know, it's hard on the head. It's hard on the head. So let's learn it together. If you want to follow along, Alchemy University, it's free. It's free, and if it's for free, it's for me. So it's gonna be this first one. I made a bit of a ways, just 18% the way through, but I'll be honest, I started getting into some thicker stuff. So I want to actually start from ground zero with you guys. So we'll run through the course. For me, some of the things are gonna be filled out already, but I'll just undo it, walk us through each step. And I really want to build a robust, you can see I was on Merkle trees and linked lists or nodes, I believe. But I really just want to get granular at it because right now for work, we're building a blockchain data collection protocol. And the more information that I'm like really keenly solid on, the better. And that was like hugely important for the Solidity course, right? For the Solidity series and learning how bytecode is stored on smart contracts and how it actually is stored on a granular level, right? Alongside of opcodes and a few other things. So this whole boot camp deal actually was the foundation for even the ECDSA node module bit that I have on this channel. So I really want to run through this whole thing with you guys and just do a live thing. Because one, I freaking love it. You know what I mean? I love blockchain stuff. And two, it's a completely free thing. You know, so they even have it here bolded, completely free. So you got to do it. It's completely free. Anyway, let's dive in. Let's dive in. Enough chitty chatting. Enough chitty. This is a bit of a longer series, by the way, comparatively to the Solidity one. We made quite a ways on the Solidity one, and I just want to get granular with the concepts because if you could fundamentally understand how blockchain and cryptography works at a base level, right? You could do some really cool things. And that's actually what we're doing for work. Really cool things with encryption layers and a few other things. So I'm actually really excited. So let's dive in. Enough of the chitty chatting. This is some Ethereum bootcamp kind of configuration. You got a Discord, you got a few things. If you get stuck, do your own research. Number one, just like always, try to tackle the problem on yourself. Use ChatGPT, all this fun stuff. Okay, so let's dive in. So this is just rough introduction. Let's talk about there's a blockchain and crypto video that I would highly suggest watching. But let's just kind of bird's eye talk blockchain and what it is, right? It's obviously a fancy word. You know, it sounds amazing, blockchain technology. But really at a core, when we boil it down from this end of the viewpoint here, it's an open database, right? Now with this open database, there's a lot of rules and things that can go with it. With data sharding and signing things and penny anonymity. So there's a lot of nuances with that, but let's just kind of I love taking big things, right, and making it sound dumb. That's like something I'm keenly good at, right? And I'll give an example. So here's like hashing functions, right? Oh my God, what's a hashing function? Sounds crazy. We're using the Kakash 256 hashing algorithm from the SHA-3 family. Holy crap, what does that mean? But if I just told you a hashing algorithm is a really good letter scrambler, you're like, oh. Now I'm not intimidated by a hashing algorithm. So I'm kind of doing that with the blockchain too. I'm just like, well, it's an open database. That's all it is. It's an accessible and open database. That's it. You know. Now obviously we're being nuanced about it or not nuanced about it. We're being rather vague when I describe that. So I just wanted to have a touch point of a few points on how this series is going to go. That's the goal, to understand stuff where we can just kind of water it down, distill the information to like bird's eye concepts. Because when you understand information and you can distill it to a bird's eye concept, that truly means you actually understand it. So yeah, let's dive in. So blockchain. So understand how blockchain is worth. Let's start off with some high level questions. What's the purpose of a blockchain? Why even learn all this technology? What all this stuff is? So the purpose of a blockchain is to have a networks of computers agree upon a commons of data. Plain and simple, any person or organization should be able to participate in this process. No one person or organization should be able to control the entire process. So the idea of an open database being decentralized and also trustless, that's a big thing that they just highlighted here. So no person or organization should be able to control it, meaning nobody can manipulate the data in a way that would be bad acting, of doing the rest of the protocol or the rest of the organization harms. Did not mean to scroll down there. Okay, so let's move on. Generally, the term consensus is used to describe a network coming to an agreement on the state of data. You'll hear this quite often in the blockchain space. Consensus is a very common thing. There's consensus mechanisms. There's link consensus, things like this. So that's a common word. So that's high level at blockchain. I think we tackled that pretty well. So it's an open database. It's trustless, and things are navigated based on this consensus, this agreement upon the users within this ecosystem. Okay, so we're learning more. So let's explore some other use cases for blockchain. One of them being cryptocurrency. So this is where things get a little bit confused in the public. When you say blockchain and you say cryptocurrency, sometimes those things are what's the word? Confused, conflated, confided. I'm not sure the word, but they get confused. Sometimes there's synonymous terms used in the public space, but for our understanding, we need to understand blockchain technology is this umbrella above things, and cryptocurrency is one use case of blockchain technology, right? So there's other things that we could use blockchain technology for, this idea of an open database, but cryptocurrency is just so far the financial pillar use case of it, and it's a phenomenal use case of it. So let's keep reading. Let's keep reading. And I would also argue that cryptocurrency isn't just the financial pillar. Ethereum, for instance, and we're going to diving into the EVM, the Ethereum virtual machine, that's kind of like a tool. Like cryptocurrency now transmutes from like this financial pillar into this like work pillar, right? Because Ethereum is like, we're using this thing for like work and transactions and moving data. And so I think cryptocurrency may, I don't know. I don't even know if it's like best for it potentially across time, but it's great for right now. But I don't want us to associate it with just financial uses is kind of what I'm getting at. So, okay, so why is blockchain needed for cryptocurrencies? To understand blockchain is needed for digital currencies, let's imagine a naive digital currency without blockchain. Let's take a spreadsheet and give all of our friends money. We're a good friend for that. So Alice, Bob, and Charlie are getting $10 each, or 10 whatever the currency is. Sweet. So everyone starts with 10 money. Now, Alice wants to buy something from Bob, so she says, or she pays him 5 money. She tells the bookkeeper, you, to transfer 5 monies over to Bob. So 5 units go over to Bob. So boom, now we have 10 to 5, 15, 10. Excellent. Everyone's balances are updated. All right, great. This is awesome. So at this point, we're thinking there isn't much to this whole digital currency thing. It's just kind of boring, right? Or more likely, you're considering all the problems with this scenario. So Alice, Bob, and Charlie need to trust that I won't cheat them, right? So as the bookkeeper, I need to be resistant to Bob being a bad actor in the system. He's now the cash king in this ecosystem here. So we need to keep an eye on Bob, that stingy guy. We see those sticky little Bob fingers. I'm just teasing. So Alice, Bob, and Charlie invite more friends into your currency circle, and quickly the bookkeeping becomes way too much for me to handle. If there's now 10,000 Charlies, 10,000 Bobs, and 10,000 Alices, it's a whole deal. So we need kind of 3 things. One, they're touching on the point of trust, that I won't cheat them as the bookkeeper. 2, that Charlie and Bob need a way to easily view their balances, and it helps if Charlie can see Bob's balance and Bob can see Alice's balance and vice versa, and everyone can see each other's balances, because then everyone's being honest. At least you can integrate that feature into your system. So now Alice, Bob, and Charlie again, and then the third point being the scalability problem. So we know how to solve programs 2 and 3, or problems 2 and 3. We could build a website with an awesome UI and an API for making transactions. But what about problem 1, the trustless situation? That is fundamentally cryptography. That is Diffie-Hellman key exchange, folks, and we will cover that on this EVM journey. I do have a small video on it actually in the channel as well, just covering bird's eye concept, non-mathematical of Diffie-Hellman key exchange. Super interesting to me. Super interesting. So this was a problem that ate at the cryptography enthusiasts for years. Deep down, many self-proclaimed cyberpunks felt as though the solution was somewhere in the land of cryptography technology, yet nobody was able to create a foolproof system. It's a hard thing to do. It truly is. In 2008, such a system was imagined by Satoshi Nakamoto, was released, obviously anonymously. In this paper, they described a system that would create a peer-to-peer network, a trustless network for exchanging value, which was obviously as pivotal as it's been. Bitcoin has made it wasn't the first digital currency, by the way. This is important to note. It's not the first one. It's the first successful one. So this system would combine years of cryptographic research and game theoretical financial incentives to create a secure, scalable network. The paper describes a chain of blocks tied together cryptographically. This would later be coined the term the blockchain. So to tie this whole deal together, the blockchain was invented to solve the issue for trust because it's a problem, right? We're all humans watching this, right? I would assume, I would hope, right? And we've all been lied to. Potentially, we've all told lies. I will use myself in this case and say I'm not holier than thou. I've said a lie or two in my life, and I wish I hadn't, but I'm human. So I don't want to say that. I don't want to assume that you guys haven't. But studies go to show that more than likely all of us have probably fibbed a story, maybe just a little bit, or maybe a little white lie, or maybe potentially big ones. And to build a system that actually removes the ability to distort information is actually keenly important for financial systems and governances and things of this aptitude. So the blockchain space, and this is actually what deeply attracted me to it, is like, oh my gosh, this is where transparency is going. This is where people are going for a trustless society where we have to be honest. We have to be these things because it's literally baked into the foundation of the system. You can't lie. And I think being the victim of potential lies or distortions of information is really what a lie is. It's not fun. It's not fun. We've all been there. It's not fun. You don't like it. It's not enjoyable. It's not typically not good for any parties involved, even for the person doing it or the person receiving it. Like there's typically a short-term gain at a short-term gain at a long-term loss for both parties. So it's a short-term gain for one party. The second one usually gets burned, and then it's usually a long-term loss for both parties who were involved in that lie. So that's what's absolutely brought me into the world of blockchains, is just that honesty, like trying to, and I'll throw it in here as well. I'm a very God-fearing individual. So the idea of the Christian religion, and I don't want to push it on anybody. I'm always inviting, but never pushy, right? But the idea is we're imperfect, chasing perfection. So this is perfection. This is the idea of chasing a transparent, perfect thing. Okay, so let's dive in. So smart contract blockchains provide developers with a way to decentralize where the code runs. In this way, code can truly become a public resource. This means code can run without any direct ownership, making it censorship resistant and transparently verifiable, right? So this is the interesting part, is not only is it a trustless system, but the two parties don't even have to know each other. It's transparently verifiable with censorship resistance. So we're all very familiar with the modern world. There's times where hey, maybe sometimes the cancel culture actually makes sense. It's like, hey, that was a little too far, but there's very many situations where it is invoking on potential just first round basic amendments and first baseline human rights of the ability of freedom of expression, right? So a system like this is obviously becoming more and more of a necessity in today's world, and this is why I'm such a gun-ho person on it. So that censorship resistance, the immutable data, the lack of being able to distort data in any individual's way who's part of the system, any individual node cannot get away with doing that. That's amazing. So one important point to drill home is that decentralization isn't about the code itself, but how the code is executed. For example, let's take a quick glance at a Solidity smart contract. So obviously learning Solidity, that's one of the other series that we've tackled, understanding how Solidity works. But the biggest thing, and we're going to dive into Solidity in this EVM series, but the biggest thing of understanding blockchain technology is how it's all constructed. Not necessarily the execution of things, if you will, but we want to make sure we have the bird's eye how these things are done, because you could always transcribe code. You could always move from Solidity to Rust. I'm sure there's going to be other popular languages that roll out. If this series is useful across time, I'm sure we're going to see very, very much advancement in this space. And, it might be such that the Solidity languages are deprecated, or maybe other things are deprecated, but the concepts themselves need to be timeless and foolproof and future-proof. Okay, so let's take a look at this Solidity contract. So we're mapping some addresses to a integer value, and we're calling this variable balances. So all that is on the smart contract, we have some bytecode that's pointing to some bytecode, and we're calling it balances. So we have our wallet address that are pointing to a value on the smart contract, and we're calling it balance. So the function transfer, we're transferring an address to, so this is going to be the address who's receiving the balance and the amount that it is. It's an external payable function, or not payable, but an external function. And all we're doing is just transferring balances, or updating our balances, based on this transfer function. So we can take my wallet address 1, and your wallet address 2, or Bob or someone, right? And I can have my 10 monies, and I can send you 5 monies. And boom, that's all we're doing here. So this function, boom, is the bread and butter of ERC20 tokens, which of course we'll talk about later in this course. Perfect. You'll see there's nothing really special about this transfer function. And if you haven't seen Solidity, when I first saw Solidity, it's terrifying, right? And even to some degree, when you see huge fleshed out smart contracts, they're terrifying. But it's not that bad. It's not that bad. We can break it down, take little bites. It's not that bad. So, okay, so here we go. So the key difference which makes this code a smart contract is when you take the code to compile it and deploy it to a decentralized blockchain, meaning this piece of code, this instructions, if you will, of data and information it's existing on multiple servers and nodes across a network. So that's cool. That's what a smart contract really is. It's just a set of instructions of what to do, and that smart contract can exist across the entire blockchain that it exists on. So when you do that, the code becomes publicly available on the blockchain, and the nodes in the network will enforce the logic and of the code throughout the financial incentives, or through the financial incentives of the blockchain protocol. Pretty cool. Don't worry if that sounds a bit complicated at the moment. Not a big deal. Not a big deal, guys. We're just building blockchain protocols. A key takeaway here is that a smart contract is code that will always run the way it is programmed. So it's a set of instructions. It's your mom's recipe list where she wrote everything down, but instead of writing it with a pencil, she carved it in a piece of stone. We'll take this one step at a time, and you'll soon see how blockchains enforce those rules. Cool. I'm excited. So cryptographic or cryptography, is it cryptographic or guys, I'm not going to lie. I got a 10 on my ACT in English. So the fact that English and I used to be a songwriter, you know what? Yeah, we'll just run with cryptographic functions. Or is it cryptographic hash functions? Before diving any further, we must understand the cryptographic hash functions. Let's break down this term a bit. A hash function is a function which takes an input of any size and turns it into a size amount or output. So let's imagine a hash function that takes an input of any size and returns a 32-byte output value. So the input, boom, this, and the output is always going to be 32 bytes. So these are hashing functions. So we can put a string of like 10 letters, 32 letters, 50 letters, 18 letters, 16 letters, numbers, things like this. And we're always going to hash it to be 32 bytes long. It's just how the rules of the game are, right? At least for the EVM. So that's important also to note. So these inputs get larger from top to bottom, but they always map to an output of 32 bytes. There are many algorithms to hash functions. There's a whole bunch of them now. There's all of these: mid squares, identity hash functions, trivial hash functions, folding hash functions, division hashing, algebraic coding. There's even more. These are not all of them. There's the rainbow hash function, the Fibonacci hash function. There's a few. Okay, so the specific types of hash functions we are going to focus on are the cryptographic hash functions. These hash functions have 5 specific properties. They need to be deterministic, so it's one way input always maps to the same specific output. What I kind of don't like about it, to be honest, but maybe I'm not smart enough to know the cryptographic hash functions, but I think for security purpose, you would almost want some sort of random variance in that, where a specific input wouldn't map to the same specific output. But I don't know how you would necessarily. I'll think of some ideas, because we're actually tackling that a bit in our encryption layer as we. Anyway, okay, so pseudo-random. It's not possible to guess the output based on the output of similar inputs. Okay, so pseudo-randomness, that kind of means there's like the Caesar cipher, right? So when you talk about key exchanges, right? So there's symmetric key exchange, there's asymmetric key exchange, and then there's Diffie-Hellman key exchange. I don't know if the Diffie-Hellman key exchange is necessarily relevant to this point, but the symmetric key exchange is relevant to the pseudo randomness. So the Caesar cipher is basically like my secret message to you might be hello, and I might just bump every letter over to the right one, and that would be like my hashing function, right? If someone figured that out, that every letter is just built to the right one, and if I said hello Bob and then hello Alice, and you figured out the term hello, so instead of it, I don't know my alphabet like that, but A B C D E F G H I, you just know that each hello starts with I. It's not pseudo-random, meaning you would be able to deterministically define, like figure out the legend or the key that I was sending messages from, and it wouldn't be random. Just because if I gave you the message hello Bob and hello Alice, and everything was similar, the hellos were the same, you would probably be able to decode. If you knew that the hello was just off one word, you'd be able to decode Bob and Alice very quickly. So pseudo-randomness is important. It means if I give you a hello Bob and a hello Alice string input values, when they hash, they're going to be completely different. They shouldn't be neighbors of each other. So one way, if someone gives you a new output, you could not determine an input without guessing. So it's a one-way hashing function. It's fast to compute. It's got to be quick. It's collision resistant, meaning it's ridiculously hard to randomly generate the same exact hash again. And the SHA-256 hashing algorithm actually has, I think there's like more atoms in the universe than there is a chance of two specific hashes being the same again. So that's a powerful thing. Mathematically, that's kind of cool. So try using this SHA-256 online tool. Can you prove yourself to each one of these properties? With secure cryptographic, let's actually mess around with this real quick. So we have an input, and you're going to see here the pseudo-randomness I'm talking about. So if I say hello Bob, look at this hash. It's ridiculously different than if I do hello Alice, right? So hello Bob was 2D6A12 ends with 90003, and then if we do this, hello Alice, D76 ends in 3. Completely different thing, even though they both start with hello. So that's even if we just change this hello to like hello 1 to hello 2, you could see how ridiculously different these hashes are. So that's super important for security here and safety. Okay, so let's keep moving forward. With a secure cryptographic hash function, you can create a unique fixed size representation of an input regardless of its size. For blockchains, this feature is critically important for saving space. In many cases, blockchains and smart contracts will not need to store an input. They can just store the hash output. Cool. That's awesome. So cryptographic hash functions will also be super important for the first successful blockchain consensus mechanisms. We'll talk about proof of work. That was a mouth. This is a lot. This is a lot to digest. This is a lot to handle. So let's try to go to our cryptographic hashing stuff. I've actually done a lot of these already. So let me just look at it real quick so I can not be totally lost. So that'll kind of be the first bit for me. I have a bit of a talking advantage, if you will, going through this series with you guys, where I'll be like, hey, I know what I'm doing here or I should in theory, because I've gone through a bit of the course already. But towards the end of it, there's some new concepts and things that I'm unfamiliar with. So Merkle roots was a new thing that I didn't understand, but probably a brilliant thing to integrate. So cryptographic hash functions, SHA-256, are one-way hash. This means that if you have an input, it's relatively trivial to find the output. Guys, I'm debating if I should just park it here. We'll have the coding session on the next bit, because we just went over a ridiculous amount of information, right? Of what blockchain is, kind of the bird's eye concept of hashing functions, all these things. So I think I'm actually going to park it here, and let's do another episode right after this, so you guys are like, we separated out, it's segmented. Maybe we'll do that with all the talking ones, because they kind of split them up into talking points, and then there's coding points, talking points, coding points for very many of them. So maybe that would be advantageous for us. So let's kind of start that. I don't know if it'll be consistent across the entire series, because we have a long series to go, but let's at least start. Yeah, some of these don't have talking points, it looks like. So yeah, let's do that. Let's separate them as best we can. But yeah, so just bird's eye concept. Looking back at the talking point of blockchain and crypto, there's a lot to unpack here. There's a lot to do, a lot to learn. So super excited to just offload this information. Again, this Alchemy University is free, is completely free to do it. It's a free resource for right now. I hope they keep it that way. I think they will. They're fantastic. So it's just alchemyuniversity.com. This is not a sponsor at all, but this is by far one of the most comprehensive cryptography courses and EVM courses that I've ever seen. So Solidity course was amazing, and I can't imagine this blockchain and EVM course being any less amazing. So I strongly encourage you, follow along, get an account. It's free, and it's amazingly good knowledge. Yeah, let's dive in together. I will see you on the next one. Cheers.